Okay, let's see the general description of displacement. And displacement is just difference between two material position. So here we have two body. First body is initial body. So for the first time we have initial body, and after some time this body have some displacement. It means it's deformed and moved. Here, the old position, which consists of the initial body, can be described by the position vector x. This is a material position vector. Okay? And then this point will move to the other point. This is new point described by the lowercase x. Okay? And the difference between big X and small x is displacement. So U is a displacement vector calculated by current material position minus initial material position. This is a concept of displacement. And then we can think the current position is a function of initial position, right? Let's look at this. Between the position in current configuration and initial configuration, there are some mapping relationship, right? So all the points in initial configuration can be mapped into some point in current configuration. So we can think some function between initial and current. So here the very important concept is that the current position is a function of initial position. Okay? So let's see. The initial position is a vector. So it has a three components, x1, x2, x3. And initial position is also vector. So x1, x2, x3. So this is a vector function. So this one line of equation means three equations. So x1 equal function of x1, x2, x3. x2 equal x2, x1, x2, x3. Similarly, x3, big x1, big x2, big x3. Okay? This vector function means this three scalar function. Okay, understand? Then we know the chain rule. Let's use chain rule. dx1 equal plus this is a well-known chain rule. Here, let's look at the first equation. dx1 means small difference in x1. Okay? Can be calculated by these three parts. first part is that small difference due to the here uppercase x1, and second part corresponding to this one, third part this one. This is a very well known chain rule. Watch this. What is this? This is some slope in big x1 direction of function x1. Okay, so this is something like that. So you remember the function f. Okay, let's say function f is this, and this is x. So this is slope. Slope means part dx df. Okay, and in this slope, if I multiply delta x, you can find delta f. Delta f equal dx df delta x, right? So this is some small increment in x1 direction. This is x2 direction, x3 direction. This is a very well known chain rule, and we can understand this equation physically, right? Similarly, we can also calculate some small difference. Well, you can think this is some increment, small increment in x2 equal partial x1 x2 dx1. This means partial derivative, right? Because the function x2 is function of big x1, big x2, big x3. So we can take the derivative for x1, x2, x3 differently, right? So we need to use a partial and plus and then we can have one more equation, finally, x3. Right? So this is just chain rule. And then let's look at this equation. And I like to write down this equation in matrix form. So dx1, dx2, dx3 equal some matrix here. dx1, dx2, dx3. Something like this, right? So we can have a 3 by 3 matrix. Okay, and we are saying, let's say this is a matrix F. And this is a vector, material vector. This is a material vector. So this is a material vector. Material vector. Initial. This is current material vector. So here the matrix F gives us the relation between current material vector and initial material vector. And name of this is a deformation tensor or deformation matrix. Let's say just deformation matrix. Okay, so let's see physically what does that equation mean. Let's say at this point we have a very tiny small material vector dx. Okay, this material vector have a direction, but its magnitude is very small. And after some time, that material vector will move and its direction will be changed. This is a dx. So the relation between the material vector in current initial configuration and current configuration is that equation. So deformation matrix gives us the relation between both. So for example, this is rubber panel. You put the very small Scotch tape here. You attach it here. And you can give some deformation. And then direction of that tape will change and the length of that tape will change. Right? This is just physical concept. Okay, so you understand the concept of a material vector and material point and deformation tensor. So let me write down that equation a little bit differently. So dx F dx here we can write down the different form x dx. Yeah, let's look at here. You never seen before this kind of equation, right? Vector, vector, right? This is vector function. You take the derivative about the vector also. Same thing. And in tensor form, dx I equal f, let's say small f, f ij dx j. Oh, sorry, we don't need to have an arrow here. And f equal f ij EI multiply EJ equal XJ XI EI EJ, something like that. So here Fij equal Xi. You can write down the same equation with a tensor. People like to use this equation. Now, let's look at this. Xij here. This is a case I equal 1, j equal 1, right? This one, I equal 1, j equal 2. I equal 1, j equal 3. I equal 2, j equal 1. So this makes sense and it's correct. Okay. Let me give you an example. Let's say we have a 2D. Let's consider 2D deformation. 2D deformation. Yeah, let's consider 3D deformation. Okay, X1, E3, E1, E2. Initially, we have a body, looks like this cube. This is an initial body. It has a height h and length L with W. Maybe B is better. B. This is initial body. Body at initial configuration. And after some time, this body will be stretched. The height decrease and width is same and length increase. And length. One plus alpha L. and material position corresponding to initial x1, E1, x2, E2, and current. Plus x3, E3. Here, we need to calculate the mapping relation between both. So x1 equal what's this? Can you find the function? x2, x3. So, first of all, I like to find the function. So, current material vector, position of material vector, position of a material point is a function of initial position, right? So, how can you find, right? This is very simple geometry. Can you do that? Yeah, for example, 1D case. Let's say this is 1D, x1, E1. We have initially bar here from 0 to A. This is a point x equals 0. And this bar is stretched to B. Okay, what's the mapping relation? This is a x, this is x. X equal A over B x, right? Let's put the x, this big X is 0, 0. Small big X is A. Then you have a B. You know? So this point move to this point, and this point doesn't move. Something like that. So one plus alpha x1, 1 minus beta x2, x3. This is function mapping. Okay, then I like to give you 3 minutes. Then you can calculate the deformation matrix, deformation tensor. Also, we say deformation gradient. Yeah, I want to give you 3 minutes. You can calculate that 9 component of deformation matrix based on this mapping. We know the equation here, right? Yeah. Okay, 정호. You know, this lecture is recorded, so maybe the student in the world, all the people in the world will watch your answer. How did you calculate the components F11 over there? How did you calculate? Yeah, put I equal 1 and j equal 1.
Because of this rule, I use it.
This rule? You don't need to use this rule. I already gave you the function here, right?
Yeah.
So, yeah, let's look at. So, first term, F11 equal. What's this? We have equation over there. Yeah, this is here. Okay, so what's this? 1 plus alpha x1. This is x1. What's this? This is just high school mathematics, right? You know, you don't know how to take the derivative of this function about this? Huh? Yes. Okay, then you need to change the old equation. And then if you take the derivative, this is partial derivative about the x2, then what you can have here. Second term, what's this? What's the number over there? So you need to calculate this one, F12, x2, x1, x2. What's the value over there? This is partial derivative. You don't know? Really? Okay, then, yeah, let me test you. So here function, x square. Watch this. When x and y are independent to each other, what function of this? What's the answer of this? So watch this. Watch this. This is 0, right? So this is all the 0. So we have 0, 0, 0, 0. 1 minus beta. Okay, so you need to study about the partial derivative. Okay. Okay. So now we defined the deformation tensor. Deformation tensor is very important. Now let me look at the volume change. Once the body is deformed, in general, volume will be changed. Okay? Total volume can increase, also can decrease. Now, let me think how we can measure that increment. So, let's say this is your initial body, and this is the current body. So its domain, omega, domain, omega, total the omega volume is omega t. Let's consider very small volume here with a cube. This is a d omega. How can we define this volume? Very small cube volume. How can we define? So we can define the volume with a 3 vector, right? Once we know 3 vector, we can define the volume. Let's say we define this volume with a vector d x1 d x1 d x2 d x3. And this volume will be changed here. Okay, something like that. This is also a very small volume, d omega t. Let's say this volume is defined by dx1, dx2, dx3. And let's say this is the material volume. So the initial material volume can be calculated by three vector. dx1 dot product dx2 cross product dx3. So there is a three vector which defines some volume. And we can calculate the volume by a one dot product and one cross product. This is a very well known basic mathematics. Also, current volume can be calculated by three vector. Right? And here we know the dx1 equal f we know the relation between material vectors at initial configuration and current configuration. Okay? And let's put this result, plug in these three equations into here. Then d omega t equal f So here, this equation become like this. Same thing. This is also basic mathematics, one of the basic mathematics. You can easily find why this relation happened through some mathematics book about geometry and vector. So, what's this? This is a determinant of deformation tensor, deformation metric. You know how to calculate determinant, right? And determinant gives us the relation between initial volume, very, very small initial volume, and very, very small current volume. So, okay, so final relation is that The ratio is something like that. Determinant F, okay, equal D this is our final result. Okay, then how about the current volume? How can we calculate the current volume, total volume? We need to take the integrate d omega. This is current volume. Initial volume. Current volume equal d omega t, right? Okay, then how about this? This equal, instead of this, we put the determinant F d omega. Then determinant F d omega. We can calculate the current volume from the initial volume, right? With this equation. Example. Do you remember the deformation tensor F? For the example, we studied before 1 plus alpha, 1 minus beta, 1, and others 0. What's the determinant F? One plus alpha, 1 minus beta. Okay, so initially our cube have a dimension L multiply H multiplied with B. This was initial. Current equal L and then this dimension was changed. 1 plus alpha L multiply 1 minus beta H multiply B, right? And then here d omega t equal 1 plus alpha 1 minus beta, right? So we arrived at the same result. Okay, any question? So concept of deformation tensor, well, deformation gradient, deformation matrix, all the same thing, are very important. First of all, we need to understand the concept of material position, material vector, and then we need to understand there exists some mapping relation between the initial and current configuration. Then we can do a lot of things. We can calculate, for example, the volume change. And then in the next class, I'm going to introduce the further topic about the deformation. Thanks.